The first lab involves using an online radioactive decay simulator. Once the simulation has run its course, you should be able to download the results as a CVS file that is readable using Microsoft's Excel. The data table for this lab requires two pieces of information from the simulator: the half-life and the initial number of particles, which you should record. You can graph your data by hand or use Excel or other spreadsheet software. If you do the graph by hand, make sure to follow the instructions provided in the video for doing handmade graphs, scaling your axes so that they cover most of the graph paper you are using. If you use Excel, import the collected data. The horizontal axis, the x-axis, will represent the time, while the vertical axis, the y-axis, will represent the number of remaining nuclei. Remember when using Excel that the data to be plotted on the horizontal axis must be the first column listed, and the data to be plotted on the vertical axis should be the second column listed. When the graph is complete, the data points should exhibit a smooth downward curve, reflecting the exponential nature of radioactive decay. You can use Excel's option of trend line, more options, to fit an exponential curve to the data points and to place on the graph the equation provided by Excel for that fitted curve. The number that appears in front of the x variable in the exponential will be the decay constant lambda. Lambda quantifies the decay rate. A higher lambda value specifies a faster decay process, resulting in more rapid decline in the number of particles. Half-life refers to the time required for half of the initial population of radioactive nuclei to decay. This crucial parameter can be calculated from the obtained lambda value using the formula natural log of 2 divided by lambda. Alternatively, we can determine the half-life graphically. On the scatter plot, a horizontal line can be drawn at the level corresponding to half of the initial number of particles to the fitted line. A vertical line drawn from this point down to the horizontal axis will provide the time it takes for half the nuclei to decay. This x value would be the half-life. We will compare the half-life values obtained from the equation and the graphical method. Ideally, these values should be in close agreement, providing validation of our understanding of the decay process. An alternative approach to extract the decay constant lambda exists. This method involves taking the natural log of the number of remaining particles for each data point. In Excel, in a column next to your initial count data, you can type equal natural log cell number, where cell number is the cell that has the number you want the natural log of. Plotting these natural log of nuclei values on the y-axis against the corresponding time on the x-axis should yield a linear relationship. Fit a line to the data and have Excel provide an equation for that fit. The equation of this fitted line contains the decay constant lambda. From there, you can calculate the half-life. Find the percentage difference between the half-life found from the equation of the fit of the first graph to the half-life found for this one. The rest of the lab uses simulations for various decay processes, including alpha decay, beta decay, and nuclear fission. These simulations will allow you to observe the dynamics of each decay type firsthand. Key aspects to focus on include the shape of the decay curve, the approximate half-life, and any unique characteristics specific to each decay process. Record your observations for each simulation in your calculations page, clearly indicating which description fits which process. Your completed Word write-up should include the completed data table and answers to the questions. There are two graphs. All graphs should have lines fitted to the data, curve or straight line as appropriate. If you use Excel, include the equation Excel provides for that fit. Each graph should have proper titles, proper labels on each axis, and in the case of any fits that tend toward the y-axis, an extension to the y-intercept. A calculations page should also be included with the calculations and reaction descriptions as specified in the analysis section.